Let's take a look at this question right here. It's problem 1 from the old exam problems, and it covers things like stress, material deformation, and Poisson's ratio, so a couple different units. We're told that we have a 40-pound lamp suspended by cables AB and BC, each having an initial length of 5 feet. So we can see that this whole system here is symmetrical. We're told that cable AB is made of aluminum, and we're given the material properties, Young's modulus, and Poisson's ratio for that. And we're told that cable AC is made of steel, which is this cable right here. And again, we're given Young's modulus and Poisson's ratio. We're told the initial diameters for AB and AC are 0.1 and 0.05 inches respectively. The questions here ask us to calculate the normal stress in cable AB and AC, to determine the change in lengths of AB and AC, and to find the changes in diameter of AB and AC. What we can see this is all going to relate to is that stress is force over area. So the first step that we're going to need to do is draw a free body diagram of this system and solve for the forces in cables AB and AC. Once we figure that out, we'll be able to calculate all of these different things right here. So let me get started with the free body diagram. So, as I was explaining, the first step in this problem is to draw a free body diagram. So we've got cable AB and cable AC both pointing upwards, and we've got the weight of the lamp pointing down. Now, the first thing that we really need to figure out is what is the angle of both of these cables. And because our system is symmetrical, we know that the angle of AB and the angle of AC will both be the same. So if we look up here, we can see that the total width between the two cables is 8 feet, which, given that this system is symmetrical, we know that the distance on the left is 4 feet and the distance on the right will also be 4 feet. What this tells us is that we've got 4 down here. 5 is the hypotenuse, so if we do some thinking, we'll recognize this as a 3, 4, 5 triangle. And that's going to be the case for both AB and AC. Now that we know the geometries of both of the cables, we can do some of the forces in the X and some of the forces in the Y to calculate the forces in both of the cables. And I'll do that right now. Once we write out some of the forces in the X, we can see that we have negative 4/5 AB plus 4/5 AC. So we've got the X component of AB going to the left, the X component of AC going to the right, and we can see that because they're multiplied by the same factor, those two values are going to have to be the same. What we can then do is write our sum of the forces in the Y. We'll set this equation equal to 0. So we've got 3/5 AB plus 3/5 AC minus the weight of the lamp going down of 40 pounds. So plugging this in down here for AB or AC, it doesn't really matter. What we're going to find is we've got 6/5 AB is equal to 40. And as a result, with a little bit of math, we find that AB equals AC both equal 33.3 repeating pounds. So we can just double check our answer, like thinking if this makes sense. Our lamp is 40 pounds, so the fact that our tension is roughly the same order of magnitude, 33, makes some sense. And it doesn't seem too low or too high to be crazy. Like if we got the tension in each cable was 1 pound, that would not make any sense. If we got that the tension in both cables was 200 pounds, that should also make us a little bit confused as to whether or not our answer is right. So now that we think that our answer is pretty good, we'll move on to part A, which asks us to calculate the stress in each cable, both AB and AC. So I'll write that up on the board now. So to calculate the stress in each cable, we know that we're going to use the equation for stress, which is force over area. We know the amount of force in each cable is 33.3 pounds. We now just have to factor in the area. Now we've got the equations for stress of AB and stress of AC both written out. We've got the tension in each cable, 33.3 pounds, divided by the area. And I'm using the equation of pi over 4 times diameter squared to get us the answer. So for cable AB and cable AC, we now know the stress by just completing these calculations here. So with a bit of math, you can see that the stress in cable AB is 4,239 psi, and the stress in cable AC is 16,959 psi. Now what we'll do is we'll move on to part B, which asks us for the change in length of each cable. So to calculate the change in length for each cable, we're going to use the equation change in length is equal to FL over EA. This equation here comes from the rearrangement of the Young's modulus equation. So if we look, we know the force in each cable. We know the initial length, 5 feet for both cables. We'll probably need to convert that to inches. We know the Young's modulus for both cables. It's given to us in the problem statement. And we also know the cross-sectional area for both of our cables. So what I'll do now is I'll write out the equations for both of these, AB and AC, and we'll see what we get. So I've written the equation out for change in length AB. We've got 33.3 pounds times 5 feet times 12 inches per foot. That way we have everything in inches. Divided by 10 times 10 to the 6th psi times pi over 4 times 0.1, the diameter of that cable, squared. And what we're going to find is that we can calculate the change in length of AB. What we find is that the change in length of cable AB is 0.0254 inches. Now we can repeat the process for cable AC. But before we do, I want to point one thing out to you that's a little interesting or could help you solve these problems faster in the future. If you look at the change in length equation, you've got FL over EA. F over A, we already know, is stress. And if you look, that's what we just calculated in part A. So rather than, plugging in 33.3 pounds over the area like we just did right here, what you could do is you could actually just plug in the stress that you had in the first part. So another way to write this equation here is that the change in length is actually equal to stress times L over E. That's another quick way that you can do these problems. So I'll set it up with this equation for cable AC and we'll solve for the change in length. So by setting the equation up that way, what you can see I did was I took the stress of cable AC, 16,959 psi, and I multiplied that by 60 inches, which is the length of the rope or the cable in inches, divided by the Young's modulus, 30 times 10 to the 6th. When we do that, we get that the total change in length of cable AC is 0.0339 inches. So when we compare the two change in lengths, the change in length of AC versus the change in length of AB, we see that the change in length of AC is greater than that of AB. What that'll mean in the physical system is that the system will move down and to the left. So that's the answer to part B, is we know the deformation in both cables and we know that the system will move down and to the left. Now we're going to compute the change in diameter of both of the cables. And the way that we're going to do that is with a little piece of information we were given at the beginning, which was Poisson's ratio, that little V-looking shape. So let me write down the definition of Poisson's ratio and then we'll solve the rest of the problem. For Poisson's ratio, we know that it's the transverse strain over the axial strain. And we know that Poisson's ratio is technically a negative. So what this tells us is that to solve for change in diameter, all we have to do is use the Poisson's ratio we were given, the initial diameter, which we were given for both cables, and the change in length, which that's what we just calculated, and the initial length, which is what we already knew. So it's fairly easy for us to set up this equation for both of the cables, and I'll write that on the board right now. So I plugged in all the values into our equation for Poisson's ratio for diameter of AB, and what we can see is we've got the change in diameter of AB over 0.1 divided by the change in length over the initial length. We'll get that the change in diameter of AB is going to be 1.41 times 10 to the negative 5 inches. And it's important to realize that because both of our cables are in tension, this value here will be negative. And plugging in pretty much the similar numbers for cable AC into this exact same equation, you'll see that on the solutions that I post. You'll get that the change in diameter of AC is negative 8.475 times 10 to the negative 6 inches. And that's it. There you go. That's how you did this old exam problem.
Let's take a look at this step drop problem right here, which is problem number 4 from the old exam problems. What we're told is we've got two cylindrical sections, AB, which is made of steel, and we're given all the specs of that, and BCD, which is made of aluminum, and we're given the specifications of that. What we can see is we've got a 15 kip load applied to the top section, two 4 kip loads applied right at the junction, and two 8 kip loads applied right at this thin plate. We're asked, with the loads applied as shown, we're told that the magnitude of change in diameter of section CD is 1.6 times 10 to the negative 4 inches. And we're told to neglect and ignore the thickness of this collar
as well as its weight in our analysis. Questions we're asked are A, B, and C. Determine the normal stress in sections A, B, B, C, and C, D. Determine the total change in length of A, B, C, D. And we're asked to determine if it increases, it stretches, or if it decreases, it gets smaller. So we'll have to figure that out. And question C is determine the Poisson's ratio for aluminum for section BCD. So what we'll do now is we will look at all of these three questions here. And what we can realize is that question A, when it's asking for stress, is going to involve force over area. So what we need to first figure out is the force, tension or compression in each one of these three sections. So what we need to do is make a section cut through each section AB, BC, and CD. And I'll do that right now. So I've got my handy dandy red pen here, and I've drawn a section cut through AB, BC, and CD. And I've included arrows that face up because in my problem, I'm going to consider each of these section cuts to be looking up. The reason I do that is so that we don't look and include the fixed support down here at the bottom. The reason is that technically speaking, this would have three reactions. It would have a force on the Y, it would have an X force, and it could have a reaction moment. So I don't want to have to solve for any of that stuff. I want to just look up and see only the forces that are applied, and that'll make my life a lot easier. So what I'll do now is with these three section cuts, right here in this bottom section of my paper, I'll draw the free body diagram for each section, and then we'll solve for the force in each part of the rod. So you can now see I've drawn the free body diagram for section AB, BC, and CD. I've drawn this little wavy line down at the bottom just to show that it's a segment cut, but I forgot to do it down here, but either way, that's what that means. As you can see, I've drawn PAB, PBC, and PCD all coming out of their particular rod section. This will be assuming that all of these rods are in tension. So if we find that we get a negative answer here, here, or here, that just means that we should have drawn our arrow pointing up, and that would indicate that our section right there would be in compression. So now what I'll do that I have the three free body diagrams is I'll write the sum of the forces in the Y direction for section cut AB, BC, and CD. And let me do that now. So I've now written the sum of the forces in the Y for all three section cuts. If we look at the section cut AB, you would get that the sum of the forces in the Y would be equal to 0, would be 15 kips up minus PAB down. This tells us that we get a positive answer for PAB of 15 kips, which means that it's in tension. When we look at the section cut for BC, we've got 15 kips going up, 4 kips going down, 4 kips going down, and PBC going down. So we've got 15 minus 8 minus PBC. This tells us that PBC is 7 kips, and because we get a positive answer, we know that it's a tension, T. When we look at this section cut over here, section CD, we'll see that the sum of the forces in the Y is going to be 15 up, minus the 2 4s going down, minus these 2 8-kip forces going down here, and minus PCD. So you'll see we've got all of that in our equation right here, and we actually will get a negative answer for PCD, which means that it is in compression. So that's why I put a little C right there, and if we want to, we can put a negative, but to me, I don't really care when I look at the answers to this. As long as you've got this circle here, I know whether your answer means tension or compression. So now that we know the force in each section of the rod, we can answer part A, which is to determine the normal stress in each of the section cuts. So let me write out the formulas for that and show you how I would proceed. Now we'll look at part A, which is to solve for the stress. We know that the equation for stress is the normal force in each section of the rod, P, divided by the area of each cross section. So we know the diameter of every cross section. So given what we just did here and using our equation for stress, we'll be able to solve for the stress in each section. And I'll write out those equations right now. So I've now taken the P of each section, cut PAB, PBC, and PCD, and divided by that cross-sectional area for each section. So what we'll find we get is that for sigma AB, we get 19.09 KSI. And the reason we get KSI units out, that's kilopounds per square inch. That's because we have kips over square inch, or kilopounds per square inch. So that's why we're getting KSI out. So we've got sigma AB. Sigma BC would be 2.228 KSI. And sigma CD, because it's in compression, is going to give us a negative stress, which is negative 2.865 KSI. Now that we've got all of this for part A, we can go up here and figure out the total change in length of the whole system. So for part B, to solve for the total change in length of the system, A, B, C, D, we know that that's going to be the change in length of each component added together. The change in length of AB plus the change in length of BC plus the change in length of CD. We know from material properties that the change in length is FL over EA, Flee. We can rewrite this equation because we have F over A. We can change this equation here to be stress times L over E. Now, why might we do that? The reason that this would be advantageous here is because we already just went through this problem and solved for the stress in each section of the bars. So as a result, what we can do is we can take the values from before and now just multiply by L over E for each particular section. So what I'll do is I'll set this up for each of the bars and we'll see what we get in a second. So you can see for the change in length of A, B, B, C, and C, D, I've taken the stress we calculated in part A and I've multiplied that by the length of each section, which were given in feet. So I've converted each of the lengths to inches by multiplying the feet that we are provided in the picture over on the left times 12 inches per foot. And I divide by the Young's modulus in KSI for each of the given sections of rod, A, B, B, C, and C, D. One thing you might be wondering is, why am I dividing by KSI down here? We were given everything in PSI. Well, because our stress is in KSI, we need to have similar units on the bottom. So the way that I did this, I didn't do it for every single one, but I showed you down here that I took 10 times 10 to the 6th psi for section BCD, and I'm multiplying that by 1 KSI divided by 10 times 10 to the 3rd psi's. So what this does is this is actually going to get us the 10 times 10 to the 3rd KSI, and this actually should be 1 times 10 to the 3rd psi. So after we plug everything in right there, what we'll find is we get our answers for each one of these is 0.01527 inches for change in length of AB. That's going to be positive. It's stretching because our tension in that section is pulling the rod out. Change in length of BC is also going to be a positive value. It's going to be 0.004 inches. And for change in length of CD, because it's got a negative stress, we know that it's going to be shrinking, which will imply that we get a negative answer here, which is negative 0.00343 inches. Now what we do is we plug these three values into the equation we have here, and we'll get that the total change in length of ABCD is equal to positive 0.015842 inches. Now, the last question is to determine the Poisson's ratio for the aluminum used in section BCD. We're told that the magnitude of the change in diameter of section CD is 1.6 times 10 to the negative 4 inches. So we know that change in diameter is going to involve Poisson's ratio, which we're given for neither of them, which actually that's our question here. So we're doing this question a little bit backwards than we might normally see in the class, is not to solve for change in diameter, because we're given that, but actually here we're asked to solve for the Poisson's ratio. So let me set up the equation for that and show you how to proceed. So for Poisson's ratio in part C, we know that it is equal to the negative transverse strain over the axial strain. We know that transverse strain is change in diameter over initial diameter, whereas axial strain is the change in length over the initial length. We can see that all of this is going to be unitless, so we just have to make sure that all our units are going to match, which we'll use inches. And we can plug in everything we know for section CD, which is the part that we're trying to determine Poisson's ratio for. And CD is a part of BC, and because this is all aluminum, it's the same thing. So I plug in 1.6 times 10 to the negative 4 inches, which is the change in diameter for CD that we're given. I divide that by 2 inches, which is the diameter initial that we're given in the problem statement. I divide all of that by the axial strain, which is the change in length of section CD, which we determined was 0.00343, so this is negative down here, divided by the initial length, which was 1 foot, but in inches is 12 inches. So when we do all that, what we get down here is we're actually going to get a positive value for Poisson's ratio, right? Because we've got the whole thing was negative, and I guess that's why I wrote this in red, is so we can draw this negative as kind of the negative of the whole problem. And we've got a negative on the bottom, so those negatives cancel out, and we get the Poisson's ratio for segment CD, which is really BCD, is going to be equal to 0.279. And there are no units, so we're good to go. And that is how you approach this stepped rod problem, which essentially asks you to take the section cuts, which we do up here. We figure out we want to look up. We draw the free body diagram for each section cut. We do a sum of the forces to find the normal force in each section. And then once we knew those forces, we were able to find the stress. Using the stress from part A, we're able to solve for the change in length in each segment, which we did right here. And in the last section, we just had to solve for Poisson's ratio. So we used our equation right here, plugged and chugged all the numbers that we had been given and solved for in the previous steps. And we get our final answer right there. So there you go. Let's take a look at this truss problem, which is problem number 4 from the old exam problems. We're told that we have a howe roof truss. There's a pin connection at A and a roller connection at G. We're told that all the forces are applied as shown. We've got the geometries of the bridge, and we're asked two questions: to identify all zero force members, if any, by inspection, and to find the forces in CD, CK, LK, BC, and BL. The number one step that I like to do in every truss problem is take a highlighter and highlight the members that we need to solve for. So we need to solve for CD, CK, and LK. So I'll highlight those here. CD, CK, and LK. And we're also asked to solve for BC and BL, which are BC right here and BL right there. So now we can see that all of the trusses members that we're looking to solve for are over here on this leftmost side. This is going to tell us how to solve the problem. And what we should try and do is take a moment of sections cut through these three members right here, because it's always very effective to try and cut through three things when you don't know what they are. So we'll draw a dotted red line, and we'll try and figure out whether we want to look to the left of this cut or whether we want to look to the right of the cut. If we look to the left, what we would see is the pin reaction forces AX and AY, and we'd see this 1,000 pound force. If we kept the cut and looked to the right, we would see 800 pounds, 600 pounds, 800 pounds, and a roller force. So we would see 1, 2, 3, 4 things. So, because we're not given the reaction forces in this problem, which sometimes on an exam you are, I'm going to decide to look left, because there are only 3 things over there, and we have only 1 x-force. As a result, I think it'll be pretty easy to look to the left and solve everything from there. So I'm going to draw my arrows over to this way, and I'm going to look left. Now normally I would have to draw a free body diagram for this whole system here to figure things out, but just to make our lives a little bit easier and to save my hand from all this writing, I'm going to take out a green marker here and draw the external reaction forces that we have acting on our truss, which is GY, AY, and AX. So these are the reaction forces that we have, and what I'm going to do is look at the whole truss to try and solve for AX and AY so that I can include that in my section cut as I move forward. So the first step now pretty much is to figure out how I'm going to solve for AX and AY. If we look, there's only one x-force here, which is AX, and one x-force on the truss, which is 800 pounds. So fairly easily you can see that if I write a sum of the forces in the x, I'll find that AX is equal to 800 pounds. So let me do that now. So after I write the sum of the forces in the x equation, I do see that AX is in fact 800 pounds, and I get a negative because I drew AX to the right. It really should have been to the left. Now I have to figure out how to get AY. Well, the best way to get AY is probably to do a sum of the moments about point G. I can't do a sum of the forces in the y for the whole truss because I don't know AY and I don't know GY, so I'd be out of luck. So the only place I can go is to do a sum of the moments about point G, and then I'll have one unknown, which will be AY. So let me set that equation up now. So what you can see right now is that I've got AY times 36, which is this distance right here between A and G. That's going to cause things to rotate clockwise, so I've made that negative. I've got this 1,000 pound force using line of action is 30 away, and that's going to cause things to rotate counterclockwise. I've got the 800 pound force. That's a distance of 9 feet away using line of action, and that would cause things to rotate clockwise. I've got this 600-pound force times 18, which is counterclockwise, so that's positive. And I've got this 800 force times 12 feet, which is also counterclockwise and positive. All of this leads me to the final answer that AY is equal to 1,200 pounds. So I'll just kind of lightly circle that answer because we probably will need that later. And now that we have AX and AY, I can actually use the section cut here that I've drawn in the dotted red line. So my next step will be to draw a free body diagram of this section cut. And I'll set that up kind of right over here right now. So what you can see is I've now drawn my free body diagram of the section cut over here. I just want to make sure that I have all the dimensions that are important. So I'll draw the height of 9 feet over here, and I'll also include my XY axes. What we can see we're going to need is we're going to need the geometry and the angles of inclination of CD and CK. So what I did was I kind of brought those over to here and drew out CD and CK so that I could kind of see these as a little bit more exploded of a view to figure out what's going on. So let's go over to our truss. If we look and I kind of put a dotted line right here, you could see that from CD, BC, and here, like we have got 3 fairly similar triangles right here. So if we know that this height, and this height are all building towards 9 feet, and that the bases are all 6 feet, we can see that this is going to be 6 and 3, 12 and 6, 18 and 9. So this tells us that the height of CD is 3 feet. And we know already from the picture that the width is 6 feet. So I just used a squared plus b squared equals c squared to find that this was 6.7 feet so that I could use similar triangles and ratios to solve. If you wanted to, you could also say that this is 26.56 degrees of theta, and that would be fine as well. For CK, what we can see is that this cuts off right there. So if this height here is 3 feet, then this height here is going to be 6 feet, and we know that the width is also 6 feet. So we get a little bit lucky with CK, and we know that the height is 6 feet, this is 6 feet, so I don't use similar triangles here. I realize this is a 45-degree angle, and I'm going to use that as we move forward. So I won't draw that on the free body diagram. I'm going to include that right there. That way it should be set up pretty good. And now what I'll do is try and figure out how to solve for all the forces. Now before we do that, question A did ask us to find all the zero force members by inspection. So we should real quick see if there are any zero force members before I move forward with this analysis to make sure that I'm not solving for something that ends up being 0. So zero force members, we want to look for a T. So anywhere where we see something that looks like this, anywhere we see something that looks like this, or anywhere we see a joint that looks like this. So it's one of those 3 things. So we can see right here at joint H, we've got a T. It looks just like this. So as a result, member FH is going to be a zero force member. Now what's important about zero force members is that if you identify this member as a zero force member, you have to remove it from the truss altogether and analyze the truss as if this member didn't exist at all. So if this member didn't exist, you would see now that JF would intersect EF and FJ in this methodology right here. So this would be a zero force member as well. And then if that was a zero force member, another domino falls, which is EJ, because then this member will be linked with the bottom of the truss as in method 1, which is the T. Therefore, EJ is a zero force member. I can't rule anything out at E. K's got a lot of stuff going on. We've got external loads at B and D and A. So if I look at C, doesn't look like any of those 3 things, so we're good. If I look down here, none of those 3 conditions either. So really the only other spot I can find any of these 3 conditions is going to be BM. So this is a zero force member. So the 3 zero force members we get using the scanning of this 3 modes is BM, EJ, FJ, and FH. So once we got that, we're good to go. That's actually none of the members that we have in question, but the fact that BM is a zero force member, as you'll see in the next page of solutions, because this is a long problem, this will actually be quite relevant because it's going to help us solve for member BC and BL a lot faster. So anyway, after we've done the zero force member stuff, we'll come back down here to our free body diagram, and see that we need to solve for CD, CK, and LK. Now, the best thing to do in a method of sections cut is to either take the moments about point K or about point C. The reason being that if we take the moments about point K, LK and CK both pass through that point, so they won't matter. If we take the moments about point C here, then CD and CK both pass through that point, so they won't have a moment through that point either. So what I did when I solved this problem was I first took the sum of the moments about point C. So by taking the sum of the moments about this point C right here, I'm getting rid of CD and CK, and I'm solving very quickly for LK. The reason I'm doing this is because LK has only an X component, so it's going to be very easy to plug this into my equation, whereas if I started with some of the moments about K, I'd have to factor in all of the X and Y components of CD, and that just seems like a little bit more work. So let me write out the equation for some of the moments about point C, which is this point right here, and you'll see what I set up. So I've now set up the sum of the moments about point C. You can see that I've got AX is multiplied by this distance of 6 using line of action, so that's clockwise. I've got minus AY times this distance here of 12, that's also going to be clockwise. Then I've got 1,000 pounds at a distance of 6 feet away, that's going to be counterclockwise. And I've got LK multiplied by 6 feet as well, which is also going to be counterclockwise. When I plug and check all of these things right here, I find that LK is going to be equal to 2,200 pounds. And because we get a positive answer here, that indicates that this member is in tension. And I will now box my answer. Woohoo! Cha-ching! So there we go. Now the next step that I would do in this question is I would sum the moments about point K. Because if I do that, then I can go and get point CD really fast. So let me set up that equation. So here I've set up the equation now. We've got AY times 18. That's going to be clockwise, so that's negative. We've got 1,000 times 12. Also going to be positive here because it's counterclockwise. And then we've got the two components of CD. So if you look at CD, CD is going to have an X component. And it's going to have a good old-fashioned Y component. And I probably should have drawn that arrow a little bit longer. Whoops! But I'll do that right now so you can see. So what we have is 6 over 6.7 CD, which is its X component based off of this similar triangle here. So we're taking the kind of red component of CD right here, and we're multiplying that by 6 because it's 6 feet right here from there to here, and that's going to be clockwise. We'll also have the Y component, 3 over 6.7, and that would really be coming from here, so that would be going clockwise around point K. So this is our Y component of CD. So that's all that we need for this equation right here. We don't include CK or LK because those pass through point K. So after I plug and chug all of this math here, I'll find that CD is equal to negative 1,192.5 pounds. And because I've gotten a negative answer here, that will indicate that my beam of this truss, CD, is in compression. Now that I've done two sum of the moment equations, the next step to do is just to solve for CK. As you can see, CK has a Y component of force. So rather than do another sum of the moments, which it's not really clear where I would do that about, maybe point D, but that would just be really messy, I'll do a sum of the forces in the Y, and I'll set that up right over here, and we'll solve for member CK. So I've now set up the sum of the forces in the Y. So you can see that we've got AY going up, which is right here. We've got the 1,000 pounds going down right here. We've got the Y component of CD, which I drew in blue. So I'll put that here. And then we've got the Y component of CK, which it doesn't really matter, honestly, because we have an angle of 45 degrees. Both the X and Y component are going to be the same. But we have CK times sine of 45, which I'll say is the purple component of CK. We can plug and chug all these numbers here because we already know CD from before. And one thing to kind of point out is we keep our free body diagram the same here. Even though we found out that CD was in compression, we don't just flip the arrow and change everything. We keep our free body diagram the same, and as a result, you see that in the Y direction, I have CD as going up. Now, we know that technically CD is going to be going down, but this gets resolved when I plug in the negative value for CD here. So that will keep everything straight, and we'll get our answer to work out. And what we find here is that CK is equal to negative 472.4 pounds.
And because we've got a negative answer, that means that our member of that piece of truss is in compression. Bum, 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 bum. So there we go. Now we got to figure out what's the next step. So we've already just solved for CD, CK, and LK. The last two that we need to solve for are BC and BL. Now if we look at our truss, we can see that BC and BL are kind of very close to this point A over here. Now what I could theoretically do is I could make another section cut here and look to the left, but the reason why that doesn't seem very appealing to me is that BC and BL both have components. So if I do any sum of the moments to solve for stuff, I'm going to have to include all these different components, and it's just going to be, in my opinion, fairly messy. One thing that helps us is the fact that we identified that BM was a zero force member. If this member is not here, then one thing we can see is that when we solve for member AB, if this member goes away, then at this joint B, we'd have only BC and BL as unknowns. So what that means I'm going to do is I'm going to do some of the method of joints right here, point A, and I'm going to solve for member AB. Once I solve for member AB, I'm going to jump to point B, and because we have two unknowns here, I'm going to again do method of joints and solve for BC and BL. So let me get another piece of paper because I've run out of space, and we'll solve for that stuff right there, and I'll show you how it's done. So now I've got my new sheet of paper here, and just to reiterate, my plan is going to be, because BM is a zero force member, I'm going to do method of joints at A, I'm going to solve for AB, and once I have AB, I'm then going to do method of joints at section point B and get BC and BL. So what I have to do then is draw a free body diagram of point A, and I'll do that right now. So here's my free body diagram. I'll include an XY axis just to be consistent. And what we can see is that AB is just like what we did before with CD. It's got a height of 3, it's got a width of 6. So we know that hypotenuse is 6.7. I use that for similar triangles. And what we can see is because I have AY, I can do a sum of the forces in the Y, because AB is the only other force with a Y component. So by doing sum of the forces in the Y and setting that equal to 0, I can very quickly see that I've got AY, which from before was 1,200 pounds, plus 3 over 6.7 AB, which is the Y component of AB right here. Doing this, I get that AB is equal to negative 2,680 pounds. And because I've got a negative answer here, that means that I've got a beam that's in compression. But as you'll see, I won't change anything with free body diagrams. I'll just keep this negative and plug it into my next set. So this was successful. I've solved for AB now, which is my first step. My second step was to do method of joints at section B and solve for BC and BL. So let me draw the free body diagram of joint B and show you how that works out. Now I've got the free body diagram of point B. What you can see is I've got the 1,000-pound force coming down on the truss. I've got member AB with its force here. I'm assuming it's in tension, even though I know it's in compression, but that'll work out. I've got BC and I've got BL here, and the geometry of all of these is the same. It's a 3, 6 by 6.7 triangle. So the two unknowns I have right now are BC and BL. So I need to write two equations to solve for those two unknowns, and those two equations are going to be the sum of the forces in the x and the sum of the forces in the y. So let me set up the sum of the forces in the x equation and show you what you would do after you did that. So I've got my sum of the forces in the x, which is 6 over 6.7 of AB, BC, and BL. AB is negative because it goes to the left, I've said, and BC and BL, I'm assuming, are going to the right, so I've got those as positive. Now, I've got all these kind of numbers here, but what I should realize is because 6 over 6.7 is multiplied by everything, I can actually factor that out and get rid of it from my equation. So I get BC plus BL minus AB equals 0. But if I take BC and BL, I can move AB to the other side, which would become positive. But AB is actually negative, so I would cancel out a little bit. But what I would see, if I solve for one in terms of the other, is that I would get that BC is equal to negative 2,680 pounds minus BL. Now using this, I just need to now write a sum of the forces in the y equation below this, and I can plug this in and solve for BC.
So I've now written the sum of the forces in the y equation. I've got negative 3 over 6.7 AB minus 1,000 plus 3 over 6.7 BC minus 3 over 6.7 BL. Something that I did just to make this a little bit easier was I divided every term by 3 over 6.7. And when I did this, given the fact that I knew AB, the equation that I more or less got was the following. So here's the equation I got. I divided everything by 3 over 6.7 to cancel that out. So when I did that, I got that 1,000 became this value right here. I brought that to the other side. I brought AB to the other side and plugged its value in. And then I plugged in this thing right here for BC. So you can see I get negative 2680 minus BL equals all this stuff here. So this gives me that BL is equal to negative 1,116.8 pounds. Because we get a negative answer, that implies it's in compression. And then I plug that value back into right here. And then I find out that BC is equal to 1,563 pounds. And that is also going to be in compression as well, because we also get a negative answer for that. So there you go. That's pretty much how you did this truss problem. It was fairly complicated. If we look back at what we did in the very beginning, you can see that we did have a lot of work to do because we had to set up the equations to solve for AX and AY. Typically on an exam you'd be given these values here, but it is good practice to understand that you can look at the free body diagram of the whole truss to solve for that. Then after that we pretty much just did a method of sections, did some moment equations about the point where members intersect, both K and C, then did a sum of the forces in the y direction, and then pretty much using our knowledge of zero force members, figured out a pretty efficient strategy to solve using method of joints for the last two members that we needed to solve for. And there you have it. That's it. All right, everyone. What I'm going to do now is go over problem number 2 from the old exam problems. Essentially, this problem initially it asked to solve for the centroids x bar and y bar for the shape shown below. What I'm going to do is I'm going to solve for both of those things, but then I'm going to add a second part to this problem, which is to solve for the moment of inertia about the centroidal y-axis. And I'll go over how to do that in a little bit after I go over this first part. So the first thing that we need to do to solve for x bar and y bar is let's just make sure we're all on the same page and write down the equation for x bar, which we know is the sum of the area of every shape times the location of the centroid of that shape divided by the sum of AI. And we know that y bar is equal to the sum of AI yi over the sum of AI. So the thing that I like to do in these types of problems is set up a table. And setting up a table will help you organize your work and make it far more easy to do the math, to keep track of everything, and solve the problem. So what I'm going to do is I'm going to set up that table and have it appear magically right here, and then we'll get started solving the rest of the problem. All right, so what I've done is I've set up a table, and the first column on our table is shape. So the first step in all of these problems, maybe after you've written your table, is to figure out how many shapes you have. So you should always be trying to identify as few number of shape as you possibly can for these types of problems. So the shapes that I identified were the triangle over here, which we can see. I can see also that we have a rectangle here had we taken out this quarter circle. So shape number 2 I've identified as this rectangle, and shape number 3 is this quarter circle. Now what I would say is, in theory, you could have done this problem and you could have said, hey, I have one giant rectangle right here, and then I have a hollow triangle and a hollow quarter circle. That would be totally acceptable to do the problem that way, because again, you would have only 3 shapes. So I highly recommend you try and find 3 shapes in the problem, and if you find any more than that, you probably have made it far too complicated, or more complicated than it was necessary. So shape number 1 is our triangle, shape number 2 is our rectangle, and shape number 3 is our quarter circle. Okay, now we just have to solve for the area of everything. Well, the area of our triangle is 1/2 the base times the height, which is 1/2, 150 times 300. The answer to that is 22,500. I'm going to go through and solve for the other areas because we'll save us a little bit of time. Okay, so I solved for the area of the rectangle. That was its base 200 times its height 300, gets us 60,000. And the area of our quarter circle, as is identified up here, is pi over 4 r squared, basically 1/4 of the area of a circle, which should make sense. We plug that in down here, we get 17,671.45. Now, something I want to point out that's actually fairly important in these types of problems is that I've made this negative. And the reason I've made this area negative is because this isn't actually a part of the shape. It's a piece that's been omitted from the overall shape. So the area should be negative. So when I add up the areas in my total row, I'll get that the total in this column is 64,828.55 millimeters to the fourth. Sorry, millimeters squared. Now what I have to do is I have to solve for xi. So to solve for xi, I'm going to be using this point right here as our datum, because you can see our y-axis goes through the shape and our x-axis is down here. Now, in theory, you can choose any datum point you want. You could have chose down here, you could have chosen up here in theory, but usually you want to choose the intersection of the xy axis because most exam questions will ask you to solve for the centroid location from each of the axes. So, for the xi, we know that the centroid of a triangle is about right here. That's going to be 1/3 the distance from the bottom side, which is going to be negative 50 millimeters. Again, because this point is 0, 0, I have to go 50 millimeters to the left or be in the negative territory to be able to do that. So now I can multiply these two things together, AI, XI, and I get that the answer here is negative 1,125,000. When I identify the XI of the rectangle, well, its base is 200. I know that the centroid of our rectangle is about right there, halfway over, so it's 200 over 2, which is 100 millimeters. Now for our quarter circle, what we can see is we're given x bar, but x bar is from the flat edge. So what we've been given for our quarter circle is essentially this distance here. But really what we want is we want this distance from the datum point to the location. So to be able to get this distance x, we'll call it xi, I guess. Xi is going to be equal to 200 minus 4 times 150 over 3 pi. And when we do that math, we get that this is 136.33. Now we can multiply AI by xi for both of these things right here. So for our rectangle, we get AI xi is 6 million. And for our quarter circle, we get AI xi, because of our negative over here, we get negative 2,409,148.78. Now we can total this column right here, and we get 2,465,851.2. Now we plug those things up here. So we plug in our 2,465,851.2 divided by our total area, which was 64,828.55, and we get that our x bar is equal to 38.04 millimeters. There we go. Now we'll do the same process for y bar. So now we just have to look at what's the yi of each shape. So our triangle, its height is right here. So our yi is this distance right there. That's 1/3 the distance from the bottom. So if the height's 300, then we have that this is going to be 300 over 3. This is equal to 100 millimeters. For our rectangle, it's 300 meters tall. So it's going to be 300 over 2 equals 150 millimeters. And last but not least, for our quarter circle, our y bar is just 4r over 3 pi, which in this case, when we're going from the flat to the location in that direction, we're actually good. We don't need to do anything special. So this is just 4r over 3 pi, which is going to be equal to 63.6. Now what we do is we multiply our area by the yi in each column again. So over here we get 2.25 million. Here we get 9 million for our rectangle. And down here we get negative 1,123,904.2. We add everything up and we get 10,126,095.78. So now we just take these numbers up here, we plug them in, and we get our answer. So we have 10,126 and 95.78 over 64,828.55. This will give us a y bar of 156.2 millimeters. So box my answer, put all that right there. And what you should always do in these problems is make sure you check your answer and that it actually makes sense. So we get x bar is 38.04. So that basically tells us that our x bar of our whole shape is about here. That is x bar of our whole shape. Now that makes sense because it seems to be about in the middle. Now if we look at our y bar is 156.2. So that tells us that y bar is a little bit up here. And that tends to make sense as well because down here we're losing this area. So our area almost should be more, our y bar should be closer to the top of our shape. Something I see students do a lot is they'll get an answer that says y bar is 500 millimeters. If that were the case, that would tell you that y bar was like up here. What are you doing? You can't have the y bar or the x bar of the shape be outside of the footprint of the shape. So you have to know that the centroid must always fall within the footprint of the shape. So I've checked our answers, at least conceptually, and it makes sense. Now what we'll do is I'll pause the video and we'll move to the second part, which is going to be this additional part to the problem I've added, which is how to solve for the moment of inertia of the shape. All right, now what we're going to do is we're going to solve this bonus question, which is to solve for the moment of inertia about the centroidal y-axis, i.e. IYC. So first question is, what is the centroidal y-axis? Well, in our last part of the problem, we solved for x bar and y bar. And we solved that x bar was equal to 38.04 millimeters. Well, what that means is that to find the centroid of our shape along the x-axis, we had to travel 38.04 millimeters to the right. That gives us this line right here. So here's our x bar, here's our line, and what this is this is the y centroidal axis. So this will be the point that we're summing our moments of inertia about. What we know is that for any system, that the moment of inertia of the system is equal to the sum of the moment of inertias of every single shape. And we know that the I of every shape, the moment of inertia of each shape, is equal to the moment of inertia of that shape about its centroidal axis, plus any adjustment factor to account for the fact it may be rotating away from that point. Okay, so what we're going to be doing is we're going to be doing the I of each shape. So we need to basically figure out the I of each shape about its own centroid plus AI di squared. So what I like to do is I also like to create a table for this system as well. Now you don't have to do this, but I like to think it keeps things organized. So what we'll do is I'll plug in our first column, which is the IC. Now, essentially what we'll be doing is we'll be finding the moment of inertia of each shape about its own centroidal y-axis, and then adding in this adjustment factor over here. So let's just write that down. So this is the moment of inertia about the centroidal axis, and this is what I like to call the adjustment factor. And this right here is known as the parallel axis theorem. All right, so let's get back to work. IC for a triangle is, if you look at your table that we'll provide you, is going to be equal to 1/36 height times base cubed. You'll also sometimes see a different equation, which is that it's base times height cubed. Now, for our triangle, we're rotating about this axis here. the triangle centroidal axes. So if the triangle got wider, it would be much harder to rotate about that axis. If the triangle got taller, that wouldn't really matter as much. That's why base cubed, as the base gets larger, the moment of inertia or the resistance to rotating goes up. So that should make some sense. Think about a figure skater as they spin. If a figure skater was trying to spin through this axis right here, I'll even draw this little picture of our figure skater. If our figure skater was trying to swing about this axis right here, as their arms got wider and wider and wider, they would spin slower and slower and slower. So the distance that matters is always the distance that's perpendicular to the axis of the rotation that you're doing. That's a way you can check to make sure that the numbers you're plugging in actually make sense. So this is going to get us, for this particular problem, 1/36 times the height, which is 300 for our triangle, times the base cubed, which is 150. This gets us a moment of inertia of a whopping 28,125,000. So that took up a lot of space, but that's all right. We don't have that much more stuff to do. Now for our rectangle. We know that for a rectangle, it's going to be 1/12 base height cubed, or 1/12 height base cubed. In this particular case, because we're rotating about this axis right here, the distance that we care about is the 200. So it's the base. So what we're going to get is 1/12 height times base cubed. This leads us to the fact that we've got 1/12 times 300 times our base, which is 200 cubed. And this gets us a value of, holy shnikes, 200 million. Now what we have to do is our quarter circle. Now this isn't found in your table, but we can see up here we've got two options. We've got Ix and Iy is 1/16 pi to the fourth, or we've got Ixc and Iyc equals this funky looking thing right here. Well, I can tell you right now that you almost never need these on the exam. The reason is because that's telling you the moment of inertia from this axis. But we don't care about that axis. We want the I-centroidal for each shape. That's exactly what we have in our parallel axis theorem equation. So what we want is we want this. And we can see that these are both the same. So for our particular case, what we're going to do is take in our Ixc, which is the same as Iyc, which is 1/16 pi r to the fourth, which is 150 to the fourth, minus 4r to the fourth over 9 pi. When we do this, what we get is that our answer is equal to 27,781,830.6. Now another key here is because this is a hollow area, we have to put a negative sign, because this is actually not really part of the shape. So to rotate this whole shape, it's going to be easier because this piece has been taken out. We have less mass in our system. Now what we'll do is we'll sum this column over here, IC, and we get 200,343,169.4. Okay, now what we need to do is, from before, we had written this column, XI. So I'll just bring that back here. We had negative 50 millimeters, 100 millimeters, and 136.33 millimeters. What we're now going to do is I'm now going to compute DI. DI is going to be the absolute value of x bar minus xi. So in this particular case, what we get is the x bar is the x bar of our shape. So for this particular case, we have 38.04 from before, minus the xi. Well, what was the xi over here? Well, it was negative 50. So we have 38.04 minus negative 50. So this actually gets us a value here that the DI is 88.04 millimeters. But what is this DI referring to? Well, Essentially, if this is the x-bar of the shape, then the di for our our triangle is the distance from here, which is 38.04 plus another 50. That's where this comes from right here. We had to go to the left, 38.04, and then to the left, 50 more. So the distance between this axis here and our centroidal axis is 88.04. And I'll put that there. We now repeat that process for the rest of our shapes. And we say that di here is 38.04 minus xi, which is 100. So if we look, what we're essentially doing here is that the distance from here to here is this distance. This is our di for the rectangle. So the distance between those two things right there is 61.96. And last but not least, down here we have 38.04 minus 136.33. And down here we get the answer is negative 98.29. Now if you forgot to do absolute value and had these as negative, that would be fine because the di is actually squared in our term anyway, so it won't make a mathematical difference. Now we're pretty much done. There's one last thing we need to do, which is to multiply the area times di squared. So now we have ai di squared. We have the areas from the previous part of the problem. The area of our triangle was 22,500 times di, which is 88.04 squared. This gets us a value of 174,398,436. Over here for ai di squared, the area of our rectangle was 60,000. So we get 60,000 times 61.96 squared. And last but not least, down here we have the area of our quarter circle, which was negative 17,671.45 times 98.29 squared. So now we've got everything in this column, so we can add everything up. And I'll just plug in these numbers right here. So for a rectangle, we would have got 230,342,496. And down here, we would have gotten negative 170,722,537. So the total in this column is 234,018,395. So, again, notice here that our moment of inertia adjustment factor is also negative. So these two terms are subtracting in the summation of all of these things. So now pretty much all I have to do is I just add this number and this number together, and I get the total moment of inertia about the centroidal y-axis of our shape, which is going to be equal to 434,361,564.4 millimeters to the fourth. And it's important that you include that unit there. Now, I find that the table is very helpful because if you combine your table from the previous part, you can keep your AI, your XI, and you would just be adding a few more columns to the right. Because usually on the exam, you won't be asked for both X bar and Y bar, you'll be asked for one or the other. So we would cancel out these two columns here. You would add in essentially this column and these two columns right here, and you would be able to get your answer much more easily and much more efficiently and neatly, which we always like when we're grading the exam. So that's it. That's how you approach a typical centroid problem. You solve for the centroid, and then you take the moment of inertia, usually about that centroidal axis. And that's it. Good luck on the exam. Let's take a look at problem number 1 from the old exam problems for buckling. What we can see is we've got an aluminum tube which has a hollow rectangular cross-section as shown here. We see that the thickness of the cross-section is t equals 3 millimeters. we're told that it's supported by pins and brackets at either end, A and B. The constraints produce a pin-to-pin connection for buckling about the z-axis, so if the beam were to buckle in this direction, kind of up and out of the paper, that would be pin-to-pin, which we know K is equal to 1. And then for the y-axis, which would be kind of it buckling almost to the left and right in the plane of the paper, we would have that the buckling would be a fixed-fixed connection because these pins here are going to prevent this portion of the beam from being able to really bend as much as they should. So we're told to assume that Young's modulus is 70 GPa and that the yield stress or the failure stress of this material is 250 megapascals. We're asked to calculate the largest axial compressive load, P max, that AB can support without failing. So what this basically means is that our beam can fail in two different failure modes. It can fail in compression, which would be the yield stress is exceeded, or it could fail in buckling. And when it can fail in buckling, it could actually buckle about the y-axis or the z-axis. Now usually, you might only need to consider one of those. But because here y, we can see that the moment of inertia of the y is going to be the easiest axis to buckle about. It's going to be lower than the moment of inertia about z. We might say, oh, we only need to consider y-axis buckling. But because the y-axis is the fixed portion, it's actually going to be more difficult to buckle about the y-axis than the z-axis. So as a result of that kind of discontinuity there, that although the moment of inertia about the y-axis is lower, its end conditions will make it more challenging to buckle. So that means we need to consider three things. We need to consider, number one, the yield stress of the beam. We need to consider buckling about the y-axis, and we need to consider buckling about the z-axis. So let's solve this problem. So to solve this problem, the first thing we need to do is look at the cross-section and set up a couple different things. What we see is it's got a height of 60 millimeters, it's got a width of 30 millimeters, and we know that the thickness is 3 millimeters. So we're going to need to take into account the outer area and the inner area together, and because we've got the y-axis and z-axis, we're going to need to compute three different things. We need to compute, one, the area. That way we can use that in our stress equation. Stress is equal to force over area. And we're also going to need to compute the moment of inertia about the y-axis and the z-axis, which we'll use in our buckling equation. So let me set all that up right now and show you what we get. So you can now see that I've set up the area equation. I've computed the area by taking the outer dimension, 60 times 30, minus the area of the inner dimensions, which, given that the thickness is 3 millimeters, is going to be 60 minus 6 and 30 minus 6. So what we calculate here is that the area of our cross-section is 504 millimeters squared. And what I then did was calculate the moment of inertia of both of the shapes. To do that, we've got I about the y-axis, which is right here. The distance about the y-axis, which is pretty much the vertical axis, if you remember, is going to be this distance here. It's harder to rotate about the vertical axis if your arms are spread out than if you're really tall. That has no effect on your ability to rotate. So that's why when you look at our equation here, we've got 1/12 height outer times base outer cubed. The cubed dimension is the one that's going to have the greatest impact. And as I was just saying, that is the width in this particular axis. So base outer is cubed. And then I'm subtracting the moment of inertia of the interior segment, which is hollow. So we take that out of our equation. So that's going to be 1/12 the internal height times the internal base dimension cubed. So when I plug those numbers in, you get 1/12 times 60 times 30 cubed minus 1/12 times 54 times 24 cubed. You'll get for IY then a value of 72,792 millimeters to the fourth. And we then repeat the exact same process for IZ. And when you're rotating about this horizontal axis here, which is pretty much this axis, it actually becomes harder if you get taller. So the dimension that ends up being cubed in this particular part is going to be the height, because that is the dimension that's farther away from that axis that makes it harder to rotate. So what we've got then is 1/12 the base outer dimension times the height outer cubed minus 1/12 the internal base times the internal height cubed. Plugging all of our numbers in, 1/12 30 times 60 cubed minus 1/12 24 times 54 cubed, we get a value of IZ is 275,072 millimeters to the fourth. So as I was explaining in the beginning, the moment of inertia about the y-axis is going to be pretty much lower than the moment of inertia about the z-axis. So when we go forward, what we're going to check now is the stress in the column to see how much stress it can take before it yields. Then we're going to check both buckling equations as well, because although we know that the moment of inertia of the y is lower than the moment of inertia of the z, the end conditions for the y-axis are fixed, which make it harder to buckle than the z-axis, which is pinned. So as a result, I'm going to check both the buckling equation about the y-axis and the buckling equation about the z-axis. Now I'm going to go back to the board and write those equations right now. So what you can see I've now done is I've written the buckling equation about the z and the buckling equation about the y. The equation is fundamentally the same for both of these examples. P critical can be calculated by multiplying pi squared times Young's modulus times the moment of inertia about the axis in question, divided by the k, which is the effective length factor, times the L, the length of our beam, all of that bottom piece squared. So we can see what we get for the z-axis is we get pi squared times Young's modulus, which is 70 times 10 to the third megapascals. And a quick little note here, we were given the Young's modulus in gigapascals, but I converted to megapascals because I like that unit a little bit better. I know that megapascals is the units of newtons per millimeter squared. That way I knew when I got an answer for this particular question, it was going to come out in newtons, and you'll see that in just a second. So we've got Young's modulus multiplied by the moment of inertia we just found, which was in millimeters to the fourth, 225,072. Plug that right there. And we divide by the length of the beam in millimeters times the k. And remember that for k is pin, we know that k is equal to 1. So we multiply 1 by 2,000 millimeters, we square that. We do all of our math over here, and we find that P critical about the z-axis is going to be 38,874 newtons, which if you look at the answer, it's actually 38.8 kilonewtons. So had we kept our Young's modulus in GPA, we would have gotten kilonewtons over here. So either way, that's fine. I then set up the equation for P critical in the y. I didn't write the equation again, I just plugged and chugged everything. So you can see we've got pi squared, the same Young's modulus, the moment of inertia that we calculated earlier. K is equal to 0.5 when your end conditions are fixed and fixed. So I plug in 0.5, multiply by 2,000, and then square that whole bottom piece. This gets us that the P critical of the y-axis is going to be 50,289. Now looking at this, what is the maximum force we can apply before the system fails? Well, it's going to be the lower of these two values. If we apply 38,874.1 Newton, then the column will buckle about the z-axis. So if we applied any more than that, the system would have already failed in this particular case. So as a result, this is currently the limiting factor, but there's still one more condition for us to check, which is going to be the yield stress. So let me write that equation up there now. What I've now done is computed the Fmax for yielding. We know that stress is equal to force over the area, where the force is P, or the normal force that's in our section. We were given that sigma y, or the yield stress, the failure point of our particular material, was 250 megapascals. So I set that equal to the force divided by the area that we calculated earlier for our cross-section, which was 504 millimeters squared. And what we find is that the Fmax to yield our cross-section is 126,000 newtons. So as a result of this, what you can see is 126,000 newtons is actually the largest force we've calculated. So the beam in question here is very, very difficult to fail in stress-related failure modes. It's going to be much easier to buckle this beam about the z-axis than it is to buckle it about the y, or to fail it in yielding. So as a result, the limiting factor for this entire problem and our final answer for what Pmax is 38,874 newtons, which is buckling about the z-axis. There you go. That's how you approach and solve this particular problem here. And just to review what we did, we first computed the area and moment of inertia for our given cross-section because we knew we were going to need that to calculate the stress and the critical buckling loads. Then what we did is we just took all that information, we set up our equations for buckling in the y and z, as well as our yielding equation, and we pretty much plugged and chugged everything we had, And we chose the lowest of all of those forces as being the maximum force, because that is the limiting factor and is the maximum you can apply before everything else fails. And that's it. Well, it's already that time again. Exam number 2. After it was so successful last time in the review session where I came to Testudo and donated my special red Expo marker, I thought I'd come back and donate another special present to ensure your success on exam number 2. This time, I thought instead of bringing a red Expo marker, I'd bring Testudo something a little bit more tasty from where I'm from. And that, of course, is a good old-fashioned Wawa Philly pretzel. Please, Testudo, help my ENES 102 students crush their second exam and be amazing engineers in the future. Good luck, everyone. I'm sure you're going to do great.